Tonight, we are going to find out how much space you actually occupy in the universe. You are standing on a planet nearly 8,000 miles wide. It feels enormous because every ocean, mountain, city, road, forest, and human life that has ever existed fits somewhere across its surface. A commercial aircraft would need almost 2 full days of continuous flight to circle it. To a person, Earth is almost impossibly large. But more than 1 million Earths could fit inside the Sun. And the Sun is only one ordinary star among hundreds of billions in the Milky Way. Our galaxy stretches so far that light needs roughly 100,000 years to cross it. Every star visible in the night sky belongs to this one structure. Every spacecraft humanity has launched, every radio signal we have transmitted, and every place our species has ever known occupies a region so small within the Milky Way that it would be invisible in an image of the full galaxy. And the Milky Way is only the beginning. Beyond it lie other galaxies separated by millions of light years. Those galaxies gather into groups and clusters. The clusters connect through enormous filaments of matter surrounding cosmic voids, hundreds of millions of light years wide. Together, they form a structure called the cosmic web, stretching across an observable universe roughly 93 billion light-years from one side to the other. At that scale, Earth does not appear small. It cannot appear at all. The solar system disappears first, then the Milky Way disappears. Eventually, entire collections of galaxies become tiny marks inside something larger. By the end of tonight, you are going to understand exactly where we exist inside this hierarchy, why every scale overwhelms the one beneath it, and how the universe can contain everything humanity has ever known without our entire world occupying even a visible fraction of the picture. The most unsettling part is that the observable universe may not be the whole universe. It may only be the part whose light has had enough time to reach us. Before we begin that journey, take a moment to like the video and subscribe to Space Like I'm Sleepy. It helps more people find these quiet explorations of the universe, and it allows us to continue traveling through places that no human body could ever reach. Now, let us return to the scale where your mind is most comfortable. Right now, your body occupies less than 1 cubic meter of space. You may be lying in a bed, sitting in a chair, or resting somewhere within a room only a few meters across. You know where the walls are without measuring them. You understand the distance to the nearest door. You can judge whether an object is close enough to touch, whether a sound came from across the room, and whether another person is moving toward you or away from you. These are distances your brain handles naturally. Human vision uses several clues to estimate depth. Your eyes view the world from slightly different positions, allowing your brain to compare the two images. Nearby objects shift noticeably against the background when you move your head. Familiar objects appear smaller as they move farther away. Shadows, texture, motion, and atmospheric haze provide additional information, but these tools become less useful as distance increases. A mountain on the horizon might appear small enough to cover with one fingertip, even though it contains more rock than every building in a nearby city. The moon appears smaller than a coin held at arm's length, even though it is more than 2,000 miles wide. Most stars appear as identical points, regardless of whether they are slightly larger than Earth or hundreds of times wider than the Sun. The human brain was not shaped to understand the actual size of these objects. It was shaped to move a human body through a local environment. For most of our history, useful distances were measured in footsteps, walking hours, and the time required to reach water or shelter. A healthy adult walks at roughly 3 miles per hour. In 1 hour, that person can cross a small town. In one day, the same person might cover 20 or 30 miles under good conditions. At that pace, even traveling around Earth would require years of continuous movement. The visible horizon reinforces this limited scale. For a person standing on level ground, the horizon may be only a few miles away. The exact distance depends on height and terrain, but the effect is the same. Most of the planet is permanently hidden beyond the curve of Earth. You never see the entire continent beneath you. You never see the complete ocean in front of you. Even from the top of a tall mountain, almost all of the world remains below the horizon. This creates a powerful illusion. The region you can see feels complete because it fills your entire field of view. A landscape reaching from one horizon to the other seems vast enough to contain the world, but it represents only a thin patch on the surface of a much larger sphere. Astronomical diagrams create a similar illusion in the opposite direction. To place Earth, the Moon, the planets, and the stars on one page, illustrators must enlarge the small objects and compress the empty distances. If they drew Earth and the Moon at the correct sizes, the page might need to be several feet wide just to preserve the gap between them. If the same diagram continued to the nearest star, the paper would need to stretch far beyond the building containing it. Later scales require even greater compromises. A picture showing the Milky Way cannot also show the solar system accurately. An image of the local group cannot display Earth. A map of the cosmic web cannot contain individual stars as visible objects. At every stage, something must be enlarged, simplified, or removed. That removal will become the central movement of this journey. We will begin with the planet beneath you, large enough that no person can see all of it at once. We will measure its widest distances and its deepest scars. Then, we will reduce it until oceans disappear, mountains flatten, and the atmosphere becomes a nearly invisible coating around a small sphere. Only then can we place that sphere beside the emptiness surrounding it. Because before Earth becomes too small to see, we need to understand how large it truly is from the surface. From the surface, Earth never presents itself as a complete sphere. It arrives in pieces. A coastline continues beyond sight. A mountain range disappears behind weather and distance. An ocean fills the horizon, even though it covers only part of the planet. No person standing on the ground can see an entire continent at once, and even astronauts in low Earth orbit see only a curved portion of the world beneath them. The planet's equatorial circumference measures approximately 24,900 miles. That is the distance around its widest part, where an imaginary line circles Earth through regions including northern Brazil, Central Africa, Indonesia, and the Pacific Ocean. A commercial aircraft traveling near 550 miles per hour would need roughly 45 hours of uninterrupted flight to complete that journey. The aircraft would have to remain at cruising speed without landing, slowing for weather, changing course, or stopping for fuel. Most passengers would experience 2 nights in the air before returning to the point where the flight began. Earth's mean diameter, measured through its center from one side to the other, is approximately 7,917 miles. The equatorial diameter is slightly larger than the distance from pole to pole because the planet rotates. That rotation creates a gentle bulge around the equator, making Earth an oblate spheroid, a sphere that is slightly wider around the middle. The difference is small compared with the full planet. Earth appears nearly round from space, but precision measurements reveal that its equatorial diameter exceeds its polar diameter by about 27 miles. Across this enormous surface, geography rises and falls in ways that shape climate, travel, borders, and human settlement. The greatest vertical extremes seem almost as impressive as the planet's width when experienced locally. Mount Everest rises approximately 5.5 miles above sea level. Its summit reaches about 29,032 feet into the atmosphere along the border between Nepal and the Tibet Autonomous Region of China. Climbers near the top enter what mountaineers call the death zone, beginning around 26,000 feet, where the air pressure is too low for the human body to adapt permanently. At sea level, each breath contains enough oxygen pressure to keep the body functioning normally. Near Everest summit, the available oxygen pressure is roughly 1/3 of the sea level value. Climbers move slowly, often using bottled oxygen, while cold temperatures and powerful winds make even simple movements difficult. The opposite extreme lies beneath the western Pacific Ocean. Challenger Deep, inside the Mariana Trench, descends close to 7 miles below sea level. Measurements vary slightly because the seafloor is uneven and difficult to survey, but the deepest confirmed regions reach roughly 35,800 feet. Water pressure there exceeds 1,000 times the pressure at sea level. Sunlight disappears far above the bottom, leaving the trench in permanent darkness. Temperatures remain only a few degrees above freezing, and vehicles sent there require thick, pressure-resistant hulls. In 1960, Jacques Piccard and United States Navy Lieutenant Don Walsh became the first people to reach Challenger Deep aboard the bathyscaphe Trieste. Their descent took nearly 5 hours. The vessel's crew compartment was a steel sphere designed to resist the crushing weight of the water above it. Everest and Challenger Deep represent humanly extreme environments. Reaching either location demands training, specialized equipment, and careful planning. Yet their combined vertical difference remains tiny beside Earth's complete diameter. Shrink the planet to the size of a standard basketball, about 9.5 inches across. Mount Everest would rise only a fraction of a millimeter above the surface. Challenger Deep would form a depression of similar scale. A fingertip passing over the model would struggle to distinguish either feature. The basketball would feel smoother than many manufactured balls because oceans, valleys, mountains, and trenches occupy such a small fraction of the planetary radius. The atmosphere would appear even thinner. Most weather occurs within the troposphere, the lowest layer of the atmosphere. Its thickness varies from roughly 5 miles near the poles to around 11 miles near the equator. Almost all breathable air, clouds, storms, and ordinary aircraft activity remain inside this narrow region. On the basketball model, the lowest 10 miles of atmosphere would form a coating thinner than a sheet of paper. Every storm ever recorded, every cloud visible from the ground, and nearly every breath taken by life on Earth would exist inside that delicate layer. Earth remains vast enough to hide almost all of itself from anyone standing upon it. Its greatest heights and depths barely roughen the surface when the whole planet is viewed at once. And beyond that surface, the nearest natural companion waits across an empty distance, nearly 30 times greater than Earth's diameter. The moon seems close because it fills a familiar place in the sky. On a clear night, its surface can appear detailed enough to study without a telescope. Dark plains mark ancient lava flows. Bright highlands surround craters formed by impacts billions of years ago. When the moon hangs near a rooftop or tree line, it can seem almost attached to the landscape. Its apparent closeness comes from angular size, which describes how much of the sky an object covers from a particular viewing point. The moon is approximately 2,160 miles wide. From Earth, it covers about half a degree of the sky. The central star appears almost the same width from our viewpoint, even though its true diameter is roughly 400 times greater. It also lies about 400 times farther away. That near match in angular size allows the moon to cover the stellar disk during a total solar eclipse. The similarity exists only from our particular location. Physical size and apparent size are separate measurements, joined by distance. The average distance from Earth to the Moon is approximately 239,000 miles. This value is measured from the center of Earth to the center of the Moon. The orbit is slightly elliptical, meaning it is shaped like a stretched circle, so the actual distance changes during each month. At its closest point, called perigee, the Moon may come within roughly 226,000 miles. Near apogee, its farthest point, the distance can exceed 252,000 miles. Most diagrams cannot show this honestly. A picture in a school book may place Earth and the Moon only a few inches apart. Their disks are enlarged so that both remain visible, while the space between them is compressed. When the correct proportions are used, the relationship looks much emptier. Imagine Earth reduced to a globe 1 foot across. The Moon would be a sphere a little over 3 inches wide. To preserve the average distance between them, that small moon would need to sit about 30 feet away. The space separating the two bodies would dominate the model. Earth's diameter fits into the average Earth-Moon distance about 30 times. The Moon itself could fit into that gap more than 100 times. A familiar comparison goes even farther. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune can all be placed side by side within the average Earth-Moon distance. Their combined diameters occupy most of the gap, with the exact result depending on which published diameter measurements are used. This does not mean those planets normally gather in a line between Earth and the Moon. It shows how much room exists between two worlds that appear close together in the night sky. Human travel makes the distance easier to feel. The Apollo astronauts crossed it using Saturn V rockets, the most powerful launch vehicles flown during the program. Apollo 11 lifted off from Kennedy Space Center in Florida on July 16, 1969. Its crew entered lunar orbit roughly 3 days later. That journey included several distinct stages. The spacecraft first reached low Earth orbit. A later engine burn sent it toward the Moon. During the coast outward, the crew traveled through a widening region where Earth gradually shrank behind them and the Moon grew ahead. Apollo missions did not fly in a perfectly straight line toward a stationary target. The Moon continued moving through its orbit while the spacecraft approached. Mission planners calculated a trajectory that would bring the vehicle to the correct region of space at the correct time. Even at Apollo speeds, the crossing lasted for days. A beam of light makes the same journey in about 1.28 seconds. That delay affected every conversation between astronauts and mission control. A message sent from Earth needed more than a second to reach the Moon. The reply then required another 1.28 seconds to return. The complete pause could exceed 2.5 seconds before accounting for human reaction time and equipment. In archived Apollo recordings, this produces moments of silence between a question from Houston and the answer arriving from lunar distance. Light travel time will become one of the most useful rulers in the rest of this journey. Miles grow inconvenient as the distances increase. Light seconds, light minutes, and eventually light years describe both distance and the delay carried by every signal. The Earth-Moon gap takes light only a little more than 1 second to cross. The distance from Earth to the body governing the motion of both worlds requires several minutes, and it opens onto a planetary system far wider than the space we have just crossed. The light crossing the Earth-Moon gap in a little more than 1 second continues far beyond the Moon. Its journey from the Sun to Earth covers an average distance of approximately 93 million miles. Astronomers call this distance one astronomical unit, a convenient ruler based on the average separation between Earth and the center of our planetary system. Sunlight needs about 8 minutes and 20 seconds to cross that distance. The light entering a room during the day began its journey several minutes earlier. When the upper edge of the sun first appears above the horizon, the light reaching your eyes has already traveled through space for roughly 500 seconds. This delay means that every view of the sky is also a view into the past. The moon is seen a little more than 1 second ago. Our star is seen more than 8 minutes ago. At greater distances, the delay will grow from years to millions and eventually billions of years. Distance alone does not reveal how completely this star overwhelms Earth. The Sun measures approximately 864,000 miles across. Earth's mean diameter is close to 7,917 miles. Placed side by side across the stellar disk, roughly 109 Earths would stretch from one edge to the other. Imagine a row of blue and white planets crossing the bright surface. Continents would vanish at this scale. Oceans would become thin color patterns. The entire moon would be smaller still, appearing beside each Earth as a small gray point. The comparison becomes much larger when we move from diameter to volume. Diameter measures the distance across an object. Volume measures all of the space inside it. When the width of a sphere increases, its volume grows with the cube of its radius. Doubling the radius creates 8 times the volume. Increasing it by a factor of 10 creates 1,000 times the volume. A star roughly 100 times wider than Earth therefore contains room for approximately 1 million Earth-sized volumes. More precise calculations place the number near 1.3 million. This assumes the planets could somehow be packed throughout the interior without gaps, which cannot physically happen. The comparison still shows how quickly three-dimensional space grows as an object becomes wider. Earth would disappear completely inside that volume. The planet's enormous circumference, its 7-mile ocean trenches, and every mountain crossing its continents would occupy a tiny region inside one ordinary star. Even Jupiter, the largest planet in the solar system, could fit inside more than 1,000 times by volume. The central star also dominates through mass. Approximately 99.86% of all the mass in the solar system is concentrated inside it. The planets, moons, asteroids, comets, dust, and spacecraft share the small fraction that remains. This concentration of mass produces the gravity that holds the planetary system together. Earth travels around the Sun at roughly 67,000 miles per hour, continually falling along a curved path rather than moving away into interstellar space. The Moon follows Earth, while both bodies orbit the much larger central mass. Deep inside the star, gravity creates the pressure required for nuclear fusion. The core reaches a temperature of roughly 15 million degrees Celsius. Under those conditions, hydrogen nuclei move fast enough to overcome much of their electrical repulsion and join through a sequence called the proton-proton chain. A hydrogen nucleus is usually a single proton. During the chain, several protons participate in reactions that eventually produce one helium nucleus. The final helium nucleus contains slightly less mass than the original particles. That missing mass has been converted into energy. Every second, the star fuses roughly 600 million tons of hydrogen into helium. Around 4 million tons of mass disappear from the final products and emerge as energy, according to the relationship between mass and energy described by Albert Einstein. The resulting power output is approximately 3.8 times 10 to the 26 watts. Written in full, that is a 3 followed by 26 zeros, multiplied by a value close to 3.8. Only a tiny fraction reaches Earth. Yet that fraction warms the surface, drives weather, powers photosynthesis, and supplies almost every food chain with its original energy. From Earth, the sun dominates the daytime sky. Seen among the wider population of stars, it occupies a much quieter position. It is neither one of the most massive stars nor one of the smallest. Many stars live far longer. Others release hundreds of thousands of times more energy before exhausting their fuel. The object large enough to erase more than 1 million Earths becomes ordinary when the full range of stellar bodies comes into view. Our star belongs to a broad band astronomers call the main sequence. A main sequence star spends most of its life fusing hydrogen into helium in its core, with inward gravity balanced by outward pressure from the energy produced there. The Sun has remained in this stable phase for about 4.5 billion years, and will continue for roughly another 5 billion years. Its surface temperature is close to 5,500 degrees Celsius. That makes it hotter and brighter than the most common stars in the Milky Way, although far more extreme stars exist at both ends of the population. Red dwarfs occupy the smaller, cooler end. They account for roughly 70% of the stars in our galaxy. Many contain less than half the mass of the Sun, while the smallest true stars approach about 8% of a stellar mass, near the minimum required to sustain ordinary hydrogen fusion. Their low mass creates enormous lifespans. A red dwarf consumes fuel slowly and mixes much of its hydrogen through the interior, allowing more of that fuel to reach the core. The least massive examples may continue shining for trillions of years. The universe is only about 13.8 billion years old, so no red dwarf has yet lived long enough to reach the natural end of such a lifespan. At the opposite end are hot blue stars with tens of times the mass of the Sun. Their cores are compressed to higher pressures and temperatures, producing fusion at a far greater rate. Some shine hundreds of thousands or even millions of times more brightly, yet their lives may last only a few million years. Extra fuel does not guarantee a longer life when the star consumes that fuel so rapidly. After a massive star begins exhausting hydrogen in its core, its outer layers can expand into a red supergiant. Betelgeuse, the reddish star marking Orion's shoulder, lies roughly 700 light-years away. Estimates place its radius near 700 times that of the Sun, with substantial uncertainty because its atmosphere swells, pulses, and sheds material. Placed at the center of our planetary system, its outer layers could extend beyond the orbit of Jupiter. Those layers would not resemble a solid surface. A red supergiant fades gradually into an extended atmosphere of gas, and some outer regions are thinner than the vacuums produced in laboratories on Earth. Astronomers estimate radius by combining distance, apparent brightness, temperature, and models of where the visible atmosphere should be defined. Each uncertain measurement affects the final result. UY, Scuti, and Stephenson 218 are often presented as candidates for the largest known star by radius. Their exact rankings remain unsettled because distance estimates have changed, their temperatures are difficult to determine precisely, and their diffuse atmospheres lack one sharp edge. A revised distance can reduce a calculated radius by hundreds of stellar radii. Physical width also gives an incomplete picture of what a star contains. When a star similar in mass to the Sun reaches the end of its life, it can leave behind a white dwarf. This remnant may hold a large fraction of the original stellar mass inside a body roughly the size of Earth. Its matter is supported by a quantum effect called electron degeneracy pressure, which prevents electrons from being compressed into the same states. A more massive star can leave a neutron star after its core collapses during a supernova. More than one stellar mass may be compressed into a sphere only about 20 to 25 kilometers across, comparable in width to a large city. A teaspoon of neutron star material is often said to weigh billions of tons under Earth gravity. The comparison gives a sense of the density, though such material could not be removed and placed on a table. Away from the crushing pressure inside the star, it would no longer remain in the same form. Stellar size therefore separates into several measurements. Red supergiants lead in radius. Massive blue stars can dominate in mass and brightness, while neutron stars reach the greatest directly observed densities. Even the broadest stellar atmosphere still occupies only one location inside a planetary system whose emptiness stretches far beyond the star itself. One astronomical unit gives us a practical ruler for the space surrounding our star. It is the average distance between Earth and the Sun, approximately 93 million miles. Mercury travels much closer, averaging about 0.39 astronomical units from the center. Venus orbits near 0.72. Earth follows at 1, while Mars averages roughly 1.52 astronomical units. These values describe the sizes of the planet's orbits, rather than a fixed arrangement. Every planet continues moving, and their positions relative to one another change from day to day. The familiar image of 8 worlds lined up beside the Sun compresses a moving three-dimensional system into a simple row. Jupiter averages approximately 5.2 astronomical units from the center. Sunlight takes more than 40 minutes to reach it. Saturn lies near 9.5 astronomical units, giving light a journey of almost 80 minutes. The distances grow more sharply in the outer system. Uranus averages about 19.2 astronomical units away. Neptune follows near 30 astronomical units, almost 3 billion miles from the Sun. Light requires more than 4 hours to travel from the center of the system to Neptune's orbit. A command sent from Earth to a spacecraft near Neptune may also take around 4 hours to arrive, depending on the positions of the planets. Confirmation that the command worked then needs several more hours to return. A complete exchange can exceed 8 hours. Mission controllers cannot steer a distant spacecraft as though it were a vehicle moving nearby. Every important action must be planned before the result can be seen. New Horizons demonstrated this during its encounter with Pluto on July 14, 2015. The spacecraft passed within roughly 7,800 miles of Pluto's surface, while traveling at more than 30,000 miles per hour relative to the dwarf planet. The one-way communication delay was approximately 4.5 hours. By the time controllers on Earth received confirmation that the encounter had begun, the spacecraft had already completed the most important part of the flyby. New Horizons followed a stored sequence of instructions. It rotated to aim cameras and spectrometers at Pluto and its moons, recorded measurements, then turned its antenna back toward Earth. A spectrometer separates light into its component wavelengths, allowing scientists to identify materials by the particular colors they absorb or emit. The mission revealed mountains of water ice, glaciers made partly from frozen nitrogen, and a heart-shaped region now called Tombao Regio. The spacecraft gathered far more information than it could transmit quickly. Its radio signal came from a transmitter using only about 12 watts of power. By the time that signal reached Earth, it was extraordinarily faint. Data arrived through NASA's Deep Space Network at rates that could fall near 1 or 2 kilobits per second, slower than the internet connections used in homes during the 1990s. Returning the complete encounter dataset required more than a year. The final portions arrived in October of 2016. An accurate scale model makes the reason easy to picture. Imagine reducing the Sun to a grapefruit about 14 centimeters wide. Mercury would become a speck less than 0.5 millimeter across, orbiting roughly 6 meters away. Earth would be close to 1.3 millimeters wide and would sit about 15 meters from the grapefruit. Mars would appear as a grain less than 1 millimeter across at a distance of roughly 23 meters. Jupiter, the largest planet, would measure only about 1.5 centimeters and would stand nearly 80 meters from the center. Saturn would lie around 143 meters away. Uranus would be almost 300 meters from the grapefruit, while Neptune would become a bead about 5 millimeters wide, positioned roughly 450 meters away. A person walking through this model would spend most of the journey crossing open ground. The planets would be difficult to notice without markers showing where to look. Gravity holds this scattered arrangement together. Each planet continually falls toward the central mass, while its sideways motion carries it along a curved orbit. Greater distance produces a longer path and a slower orbital speed. Neptune requires almost 165 Earth years to complete a single journey around the Sun. Its orbit forms the outer boundary of the familiar planetary map. Beyond that blue world, smaller icy bodies continue for billions of miles. Solar plasma flows outward still farther, while distant comets follow paths reaching into a region measured in fractions of a light year. Beyond Neptune, the major planets give way to a broad population of smaller icy worlds. The Kuiper Belt begins near Neptune's orbit, around 30 astronomical units from the Sun, and extends to roughly 50 astronomical units. It contains frozen remains from the early solar system, including mixtures of water, ice, methane, ammonia, and rocky material. Pluto is one member of this population. Its diameter is about 1,477 miles, making it smaller than Earth's moon. Other large Kuiper Belt objects include Makemake, Haumea, and Quaoar. Eris travels farther away, on a more stretched orbit, and played an important role in the decision to define the term dwarf planet in 2006. Neptune's gravity has shaped many of these objects over billions of years. Pluto completes 2 orbits around the Sun during the time Neptune completes 3. This stable relationship is called an orbital resonance. Regular gravitational tugs keep the 2 worlds from approaching dangerously close, even though their orbital paths appear to cross when viewed from above. Farther out lies the scattered disk, a more widely dispersed population of icy bodies. Encounters with Neptune during the solar system's early history pushed many of them onto elongated and steeply tilted orbits. Some travel inward toward the Kuiper Belt before moving hundreds of astronomical units into distant space. These small bodies extend the material structure of the solar system beyond the major planets, though another boundary is created by something much less visible. The Sun continuously releases a flow of charged particles known as the solar wind. Most of these particles are electrons and protons escaping from the hot outer atmosphere. Near Earth, the flow commonly travels at hundreds of kilometers per second. As the solar wind expands, it creates a vast cavity called the heliosphere. The cavity is surrounded by the interstellar medium, the thin mixture of gas, dust, charged particles, and magnetic fields occupying the space between stars. Eventually, the outward pressure of the solar wind weakens enough to balance the pressure of the surrounding interstellar material. This boundary is called the heliopause. Voyager 1 crossed the heliopause in August of 2012 at a distance of approximately 122 astronomical units. Scientists identified the crossing through changes in the charged particles surrounding the spacecraft. Particles associated with the Sun declined sharply, while higher energy particles arriving from the galaxy became more common. Voyager 2 crossed its own section of the heliopause in November of 2018, near 119 astronomical units. The different crossing distances showed that the heliosphere does not form a perfect sphere. Its shape changes with solar activity and with conditions in the surrounding interstellar medium. Both spacecraft had entered interstellar plasma, meaning the charged particles around them were now dominated by material from beyond the heliosphere. Gravity still connected them to the Sun. A much larger region may surround everything seen so far. The Oort cloud is a proposed reservoir of icy objects extending in all directions around the planetary system. No spacecraft has reached it, and no telescope has photographed the cloud as one complete structure. Its existence is inferred from long-period comets, which arrive from extremely distant and randomly oriented paths. Some of these comets require thousands or millions of years to complete one orbit. Their approach directions suggest a roughly spherical source rather than a flat belt aligned with the planets. Estimates often place the inner Oort cloud several thousand astronomical units away. The outer region may reach roughly 100,000 astronomical units, although the boundary remains uncertain. 100,000 astronomical units equals approximately 1.6 light-years. At that distance, the gravity of nearby stars and the wider Milky Way begins to compete strongly with the pull of the Sun. A passing star can alter the orbit of an Oort cloud object. The combined gravitational influence of the galaxy, called the galactic tide, can also disturb these distant bodies over long periods. A small change may send an icy object inward. Thousands of years later, it can appear near the planets as a long-period comet, producing a glowing coma and tail as sunlight warms its surface. The solar system therefore carries several edges. Neptune marks the outer major planet. The Kuiper belt marks a broad icy population. The heliopause marks the limit of the solar wind's dominance. The Oort cloud may trace the farthest reservoir of objects still loosely held by solar gravity. Voyager 1 crossed one of these boundaries after about 35 years of travel. Nearly half a century after launch, it remains thousands of times closer to the inner planetary system than to the most distant estimated regions of the Oort cloud. Voyager 1 was designed to visit the outer planets, gather photographs and measurements, then continue wherever its final trajectory carried it. The spacecraft launched from Cape Canaveral on September 5, 1977, aboard a Titan IIIe Centaur rocket. Its original mission focused on Jupiter and Saturn, taking advantage of a rare planetary arrangement that allowed one encounter to guide the spacecraft toward the next. Voyager 1 passed closest to Jupiter on March 5, 1979. The planet's gravity bent the spacecraft's path and increased its speed. Its cameras returned detailed images of Jupiter's clouds, the Great Red Spot, and several moons. The mission also helped reveal active volcanoes on Io, where eruptions send sulfur-rich material hundreds of kilometers above the surface. The spacecraft reached Saturn on November 12, 1980. Mission planners directed it near Titan, Saturn's largest moon, because Titan's thick atmosphere was one of the mission's highest scientific priorities. That close passage changed Voyager's direction, lifting it away from the broad plane in which most planets orbit. After Saturn, no additional planet waited along its path. The spacecraft continued outward at approximately 17 kilometers per second relative to our star. That equals more than 38,000 miles per hour. At such a speed, Voyager could circle Earth in well under an hour if a straight path through the planet were possible. Its outward journey has continued for nearly half a century. In late July of 2026, Voyager 1 was about 16.3 billion miles from Earth, equal to roughly 175 astronomical units. A radio signal required more than 24 hours to travel one way. A command sent on Monday afternoon would reach the spacecraft on Tuesday afternoon, and confirmation could not return until Wednesday. Communication depends on NASA's Deep Space Network, a system of large radio antennas located near Goldstone, California, Madrid, Spain, and Canberra, Australia. Their separation around Earth allows at least one complex to face a distant spacecraft as the planet rotates. Voyager's main radio transmitter uses only a few tens of watts, comparable to the power consumed by a small household light. Its signal spreads across an ever-widening region while traveling back toward Earth. By the time it arrives, the signal is extraordinarily weak, requiring large antennas and sensitive electronics to separate it from background radio noise. Electrical power aboard Voyager comes from radioisotope thermoelectric generators. These devices use heat released by the natural decay of plutonium-238. The heat passes through materials that convert part of the temperature difference into electricity. Plutonium decay and gradual equipment deterioration reduce the available power each year. Engineers preserve the mission by switching off heaters, instruments, and supporting systems whose electricity is needed elsewhere. Voyager 1 began its journey with 10 science instruments. By April of 2026, only 2 remained in regular scientific operation after the low-energy charged particle instrument was turned off to conserve power. The surviving instruments continued measuring magnetic fields and plasma waves in interstellar space. Every shutdown extends the remaining mission, though each one also narrows what the spacecraft can observe. Eventually, its electrical supply will become too weak to operate any science instruments or maintain communication with Earth. Voyager will continue moving after its signal ends. Its current distance sounds immense in miles, yet it equals only about 2.8 thousandths of 1 light year. Light crosses Voyager's entire completed journey in approximately 1 day. The spacecraft required nearly 49 years to cover the same distance. At its present speed, traveling 1 complete light year would take roughly 17,000 years. Crossing the possible outer extent of the Oort cloud could require tens of thousands of years, depending on where that uncertain boundary is placed. The nearest star creates a still larger comparison. Proxima Centauri lies about 4.24 light-years away. Voyager 1 is traveling in a different direction and will never approach it, but its speed can be used for a hypothetical journey. Covering Proxima's distance would require roughly 70,000 years. During that interval, recorded human history could repeat many times over. Languages would change beyond recognition, coastlines would shift, and the spacecraft would continue moving at the same impressive human speed. Voyager 1 remains the most distant human-made object. It has crossed the heliopause and entered interstellar plasma. On the scale separating one stellar system from the next, its historic journey has covered only the first few thousandths of the distance. Proxima Centauri carries the reassuring title of nearest known star beyond our own system. Its distance removes most of that reassurance. It lies approximately 4.24 light-years from Earth, equal to nearly 25 trillion miles. Light, moving at about 186,000 miles each second, needs more than 4 years to complete the journey. A radio message sent toward Proxima Centauri tonight would arrive sometime in 2030. An immediate reply traveling at the same speed would not reach Earth until more than 8 years after the original transmission began. Voyager 1 gives that delay a mechanical scale. Traveling near 17 kilometers per second, it would need roughly 70,000 years to cover the same distance if it were moving directly toward Proxima Centauri. The spacecraft is actually heading elsewhere, so this remains a comparison rather than a future encounter. 70,000 years ago, Homo sapiens already existed, though agriculture, permanent cities, and written records remained far in the future. A Voyager speed mission launched toward Proxima would arrive after a span more than 7 times longer than the history of farming. The model used for the planetary system makes the separation easier to picture. Suppose the Sun were reduced to a ball about 14 centimeters wide. Earth would become a speck, roughly 1.3 millimeters across, orbiting about 15 meters from it. Neptune would sit nearly half a kilometer away. Proxima Centauri would need to be placed more than 4,000 kilometers from the model star. A scale system beginning in Toronto could place the nearest stellar neighbor beyond the western coast of North America. The exact destination would depend on the chosen starting point and model size, though the order of magnitude remains the same. Between those two small model stars would lie thousands of kilometers containing no other star at all. Proxima Centauri itself is a red dwarf. It contains only about 12% of the mass of the Sun and measures roughly 1/7 as wide. Its surface is cooler, and its visible light output is so faint that the star cannot be seen with unaided human eyes, despite being our closest stellar neighbor. The star can also produce powerful flares. Magnetic energy stored in its atmosphere is sometimes released suddenly, increasing ultraviolet and X-ray radiation around nearby planets. At least one confirmed planet, Proxima Centauri b, orbits within the region where temperatures could permit liquid water under suitable atmospheric conditions. It has a minimum mass close to that of Earth and completes one orbit in about 11.2 days. Its closeness to the star creates serious complications. Proxima b receives frequent high-energy radiation, and strong stellar activity may strip or chemically alter an atmosphere. The planet may also be tidally locked, keeping one side facing the star while the other remains turned away. Although its exact rotational state has not been directly measured, Proxima belongs to a wider three-star system. Alpha Centauri A and Alpha Centauri B form a close binary pair about 4.37 light-years from Earth. A binary consists of two stars orbiting a shared center of mass. Alpha Centauri A resembles our star in mass and temperature, while Alpha Centauri B is somewhat smaller and cooler. The distance between those two stars changes as they follow an elliptical orbit, lasting almost 80 years. At their closest, they pass at a separation comparable to the distance between Saturn and the Sun. At their widest, they move several times farther apart. Proxima lies much farther from the central pair, currently separated from them by roughly 13,000 astronomical units. Evidence suggests that it remains gravitationally bound and may require around 500,000 years to complete one broad orbit. Even this nearest stellar system is therefore spread across a region much larger than the planetary system surrounding Earth. The same pattern continues throughout the local neighborhood. Stars near us are commonly separated by several light-years. Some form binaries or larger groups, while others move alone through the galaxy. Their positions in the night sky conceal these depths. Human vision projects stars at many different distances onto an apparent dome above Earth. 2 points of light may appear side by side, while one lies hundreds of light-years behind the other. The constellations are therefore viewing patterns rather than compact physical groups. Orion's stars, for example, occupy very different distances from Earth, despite forming one familiar outline in the sky. A planetary system occupies only a small region around each stellar point. Between those systems, sparse gas and microscopic dust fill distances measured in light-years. Greater speed seems capable of shortening the crossing. At a meaningful fraction of light speed, however, even those scattered particles would strike a spacecraft with enough energy to become a serious source of radiation and physical damage. Interstellar space contains far less matter than any environment on Earth, yet it still contains enough material to challenge a fast-moving spacecraft. The density changes from one region to another. Some areas contain only a fraction of one atom in each cubic centimeter. Denser clouds may contain several atoms in the same volume. A cubic centimeter is roughly the size of a small sugar cube. So these numbers describe a vacuum far thinner than anything humans normally experience. Our solar system currently moves through a region called the local interstellar cloud. It extends for several dozen light-years and contains warm, partially ionized material. Ionized means that some atoms have lost electrons, leaving electrically charged particles behind. The cloud has a temperature of several thousand degrees, although it would not feel hot in the ordinary sense. Its particles are spread so widely that very little heat could be transferred to an object passing through it. Nearby lies the local bubble, a much larger cavity of especially thin, hot gas that may have been shaped by ancient supernova explosions. Most interstellar matter consists of hydrogen and helium. Heavier elements form a small fraction, while microscopic grains of dust contain compounds built from carbon, silicon, oxygen, iron, and other elements produced inside earlier generations of stars. At ordinary spacecraft speeds, these particles are usually manageable. A vehicle moving at 10 or 20 kilometers per second encounters them with modest, relative energy. The situation changes sharply when the vehicle reaches a meaningful fraction of light speed. At 1/10 light speed, a spacecraft would travel close to 30,000 kilometers each second. A single hydrogen nucleus encountered head-on would strike with energy in the range of several million electron volts. An electron volt is a tiny unit used to measure energy at the scale of atoms and particles. A million electron volts is called a mega electron volt. Particles with this much energy can pass into materials, knock electrons from atoms, damage molecules, and disrupt electronic components. The spacecraft would experience ordinary interstellar hydrogen as a continuous stream of particle radiation concentrated on its forward surface. Galactic cosmic rays would add another hazard. These are high-energy atomic nuclei arriving from events throughout the galaxy. Some were accelerated by supernova remnants or other violent environments and move close to light speed before entering a spacecraft or human body. Their paths can cut through electronics and living tissue. Repeated exposure may damage genetic material, increase cancer risk, and produce errors in computer memory. Structural materials can also become weaker after long periods of radiation bombardment. Dust creates a different problem. A grain too small to see can carry enormous kinetic energy when the collision speed becomes extreme. A grain only a fraction of a millimeter wide could strike a fast spacecraft with the concentrated force of an explosive impact. Larger grains would be rarer, though a single collision could destroy exposed equipment or penetrate shielding. Modern spacecraft often use Whipple shields against small debris. A Whipple shield places a thin outer layer ahead of the main hull. An incoming particle strikes the first layer and breaks apart, spreading its energy across a wider area before the fragments reach the deeper structure. This method works well against small objects at conventional orbital speeds. Interstellar travel near 1/10 light speed would demand much thicker protection. Several separated layers, active detection systems, or some combination of these approaches. Every added shield increases spacecraft mass. Greater mass requires more energy for acceleration. The propulsion system must then accelerate its own fuel, the shielding around that fuel, and the equipment needed to control the vehicle. Chemical rockets face a severe mathematical limit described by the rocket equation. As the desired change in velocity increases, the required amount of propellant rises exponentially. Carrying more fuel adds mass, which requires still more fuel to accelerate. Nuclear propulsion, laser-driven sails, or antimatter concepts might reduce parts of this burden. although each introduces difficult engineering constraints of its own. Heat must also leave the spacecraft. Engines, electronics, crew compartments, and impacts all produce waste heat. In space, heat cannot escape through air or flowing water outside the vehicle. It must be emitted as infrared radiation from large radiator surfaces, which become additional structures requiring protection. Navigation grows more demanding as speed increases. A craft traveling at 1/10 light speed crosses the distance from Earth to the Moon in about 13 seconds. Detecting a small dark object only a few thousand kilometers ahead may leave almost no time to respond. Arrival creates the final major energy problem. A spacecraft accelerated to interstellar speed must slow down before reaching its destination. Otherwise, it would cross the target system rapidly and continue into space. The energy required for deceleration can be comparable to the energy used for acceleration. Carrying that reserve increases the mass from the beginning of the journey. Speed can shorten a crossing measured in years. It also transforms thin gas into radiation, dust into high-energy projectiles, and shielding into a major fraction of the vehicle. Even a spacecraft that solved every one of these problems would have crossed only a few light years, a distance too small to mark clearly on a complete map of the Milky Way. A journey of 4 light years would carry a spacecraft only from one stellar system to the next. From far enough away, both systems would occupy the same tiny region inside a much larger structure. The Milky Way is a barred spiral galaxy, a rotating collection of stars, gas, dust, stellar remnants, and dark matter held together by gravity. Its visible stellar disk measures roughly 100,000 light-years across, although no sharp border marks its final edge. Star counts gradually thin with distance from the center. Faint streams and extended populations continue beyond the brightest disk, so different surveys can produce different measurements. The galaxy fades outward, rather than ending at one clean boundary. Most of the familiar spiral pattern lies within the thin disk. This flattened region contains large amounts of cold gas and dust, along with many young stars. Dense clouds inside it can collapse under gravity, forming new stellar systems. Bright blue stars illuminate nearby gas, while dark dust lanes block visible light from more distant regions. The thin disk is only around 1,000 light-years thick near our location, though its thickness changes across the galaxy. That still leaves enough vertical space to contain the distance from Earth to Proxima Centauri hundreds of times. A thicker population surrounds it. The thick disk contains older stars following wider paths above and below the galactic plane. These stars generally contain lower proportions of heavy elements because they formed earlier, before repeated generations of stellar explosions had enriched the galaxy with elements such as iron and oxygen. Near the center, the Milky Way becomes crowded. A long bar of stars crosses the inner region. Its gravity helps guide gas inward and influences the shapes of the spiral arms extending through the disk. Those arms are broad patterns of increased density, star formation, and gas. Individual stars move through them during their galactic orbits, rather than remaining permanently fixed inside one arm. Our system lies within a smaller feature called the Orion Spur, positioned between the larger Sagittarius and Perseus arms. This location places us roughly 26,000 light-years from the galactic center, a little more than halfway between the center and the visible outer disk. A signal traveling at light speed would need about 26,000 years to reach the center from Earth. Voyager 1, moving near 17 kilometers per second, would require hundreds of millions of years to cover the same distance. The bright disk forms only part of the galaxy. A faint stellar halo surrounds it, containing old stars and globular clusters. A globular cluster is a tightly packed, roughly spherical gathering of ancient stars. Some contain hundreds of thousands of members crowded into a region only a few hundred light-years wide. Beyond the visible halo, a much larger dark matter halo dominates the galaxy's mass. Dark matter does not produce ordinary light, so astronomers detect it through gravity. Stars and gas in the outer Milky Way orbit faster than the visible material alone can explain. Satellite galaxies also move within this wider gravitational structure. The Milky Way may contain somewhere between 100 billion and several hundred billion stars. The broad range reflects the difficulty of counting faint red dwarfs, hidden stars behind dust, and objects on the far side of the galactic center. The European Space Agency's Gaia mission has transformed this map. Gaia measures stellar positions, distances, and motions with exceptional precision. One of its key methods is parallax, the small apparent shift of a nearby star against more distant background stars as Earth moves around its orbit. By comparing observations taken months apart, astronomers can calculate distance through geometry. Gaia has recorded data for nearly 2 billion sources, allowing researchers to trace stellar streams, identify clusters, and reconstruct parts of the Milky Way's merger history. At the center lies Sagittarius A, a compact radio source associated with a supermassive black hole containing approximately 4 million times the mass of our star. Astronomers establish this mass by following stars moving around an invisible central point. One of the most important is S2, which completes an orbit in roughly 16 years. Near its closest approach, it travels at several thousand kilometers per second. Decades of observations from telescopes in Chile and Hawaii have traced S2's curved path. The orbit requires an immense mass concentrated within a remarkably small region, matching the expected influence of a supermassive black hole. From the galactic center, the distance to Proxima Centauri and the full planetary system around Earth would be too small to separate on a complete map. Voyager's journey would vanish inside the same unmarked point. The entire Milky Way is moving as well. Our system travels around its center at roughly 500,000 miles per hour, yet one complete orbit requires more than 200 million years. That motion carries Earth, the Moon, and every object bound to our star through the Milky Way as one traveling system. Earth completes one orbit around the Sun in about 365 and 1/4 days. During that year, it moves at nearly 30 kilometers per second, covering close to 600 million miles along its curved path. The planetary system follows a much larger orbit around the center of the galaxy. Our star moves at approximately 220 kilometers per second, close to 500,000 miles per hour. In the time required to read a single sentence, the entire solar system may travel hundreds of kilometers along its galactic path. That speed would cross the Atlantic Ocean in less than a minute. It could circle Earth in under 2 minutes if the route followed the surface. Across the Milky Way, however, the same velocity produces very slow progress. The distance from our location to the galactic center is roughly 26,000 light-years. The complete orbital path measures far more because it curves around the center rather than traveling straight toward it. One galactic orbit takes approximately 220 to 250 million years. Astronomers cannot assign one perfectly exact value because the speed of our system and the distribution of mass within the Milky Way remain subjects of continuing measurement. Dark matter, stars, gas, and the central regions all contribute to the gravitational field shaping the orbit. The term galactic year describes this immense period. Earth formed roughly 4.5 billion years ago. During that entire span, the solar system has completed only around 20 journeys around the Milky Way. The continents have rearranged many times during a single galactic orbit. Species have appeared, changed, and disappeared, while our system advanced through only part of its path. 1 galactic year ago, Earth was near the late Triassic period. Pangaea still joined most of the planet's land into one enormous supercontinent. The Atlantic Ocean had not yet opened into its modern form. Early dinosaurs walked beside crocodile relatives, while small mammal ancestors lived close to the ground. Some of the oldest known true mammals appeared during this broad period. Large marine reptiles occupied the oceans, and conifer forests covered wide regions of land. Since then, the solar system has traveled once around the galaxy. During that single orbit, Pangaea broke apart. Flowering plants spread across the continents, and every non-avian dinosaur disappeared. Modern humans emerged during only the final fraction of that galactic year. The Milky Way changes during these long periods as well. Stars are born from collapsing clouds. Massive stars explode, and smaller galaxies are gradually pulled apart by the galaxy's gravity. Our orbital path does not form one perfectly repeated circle through an unchanged environment. Individual stars also move relative to one another. Astronomers call this apparent movement across the sky proper motion. Nearby stars often show the largest proper motions because their sideways movement is easier to detect from Earth. Barnard's star, about 6 light-years away, has the greatest known proper motion of any star in the night sky. It shifts by roughly 10 arcseconds each year. An arcsecond is a very small angular measurement, equal to 1 part in 3,600 of 1 degree. The change is invisible during a single night. Photographs separated by years reveal the star slowly moving against more distant background objects. Over tens of thousands of years, these movements alter the constellations. Orion's familiar shape will stretch and distort as its stars follow different paths. The Big Dipper will gradually lose its present outline. Constellations appear permanent only because a human lifespan captures a very short interval of stellar motion. Human technology has occupied an even shorter period. The first powerful radio transmissions began around a century ago. Since radio waves travel at light speed, the oldest signals have expanded outward in a sphere with a radius of roughly 100 light-years. That sphere contains thousands of nearby stars, yet its radius is about 1,000th of the Milky Way's width. Most of the galaxy remains far beyond anything transmitted during human history. The sphere also exaggerates our practical detectability. Radio energy spreads across a larger area as it travels. Its strength declines according to the inverse square law, meaning that doubling the distance spreads the same power across 4 times the area. Ordinary television broadcasts and communication leakage become extremely faint long before reaching the outer edge of the theoretical radiosphere. A distant civilization would need sensitive equipment, favorable frequencies, and knowledge of where to search. A century of transmission has barely entered the local stellar neighborhood. During that same century, astronomy crossed a far greater boundary. In the early 1920s, scientists were still debating whether the Milky Way contained the entire universe, or whether faint spiral shapes in the sky belonged to separate galaxies far beyond it. In 1920, the Milky Way still seemed large enough to contain everything astronomers could see. The spiral-shaped patches scattered across the sky were called spiral nebulae. A nebula was understood as a cloud of glowing gas or dust, so the name carried an assumption that these objects belonged somewhere inside our galaxy. Their true nature became the subject of a formal public discussion held on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C. The event later became known as the Great Debate. Harlow Shapley argued that the Milky Way was far larger than many astronomers had previously believed. His work with globular clusters, placed the center of the galaxy far from Earth, in the direction of Sagittarius. Within this enlarged Milky Way, the spiral nebulae could remain relatively nearby objects. Heber Curtis defended a different picture. He believed the Milky Way was smaller and that spiral nebulae were separate systems of stars located at enormous distances. Astronomers sometimes called this the island universe idea, because each spiral appeared to form its own remote stellar island. Both men had useful evidence, along with measurements later shown to be incomplete. The debate produced no immediate winner, because astronomy still lacked a dependable way to measure the distance to the spirals. Part of the solution had already been developed by Henrietta Swan Leavitt. Leavitt worked at the Harvard College Observatory, studying photographic plates that recorded stars in the large and small Magellanic Clouds. These two small companion galaxies were visible from the southern hemisphere, though their true status as galaxies was not yet fully understood. She concentrated on variable stars, whose brightness changes over time. One important class was the Cepheid variable, named after the star Delta Cephei. A Cepheid expands and contracts in a regular cycle. As its outer layers move, its temperature and brightness rise and fall. Leavitt noticed that brighter Cepheids took longer to complete each cycle. In 1912, she published a clear relationship between pulsation period and luminosity. Luminosity means the total amount of energy a star truly produces, independent of how far away it appears. A Cepheid, completing one cycle over a long period, is intrinsically brighter than a Cepheid pulsing more quickly. Once the period is measured, astronomers can estimate the star's true luminosity. They then compare that true luminosity with the star's apparent brightness as seen from Earth. A powerful lamp viewed from far away can appear as faint as a weak lamp nearby. Knowing the lamp's real output allows distance to be calculated from how much its light has faded. Cepheids provided astronomy with a similar tool and became a type of standard candle, an object whose known brightness can serve as a distance marker. The remaining challenge was finding one inside a spiral nebula. Edwin Hubble searched for such stars using the 100-inch Hooker telescope at Mount Wilson Observatory in California. When the telescope began operating in 1917, it was the largest effective telescope in the world. Its main mirror measured 100 inches, or 2.5 meters, across. Hubble photographed the Andromeda Nebula repeatedly, comparing plates taken on different nights. In 1923, he found a small point of light that changed brightness between exposures. At first, he considered several possible explanations. Continued observations revealed a repeating cycle matching a Cepheid variable. The star later became known as V1, meaning the first variable identified in that series. Its pulsation period revealed its intrinsic luminosity. Its faint appearance then supplied the distance. Hubble's original calculation placed Andromeda roughly 900,000 light-years away. That estimate was much smaller than the modern value because the Cepheid distance scale had not yet been calibrated correctly. Astronomers later discovered that different types of Cepheids follow somewhat different relationships between period and luminosity. Even the underestimated figure was decisive. The accepted Milky Way could not reasonably extend far enough to contain Andromeda at that distance. The faint spiral patch belonged to a separate galaxy. Modern measurements place Andromeda about 2.5 million light-years from Earth. The light Hubble studied had crossed intergalactic space for millions of years before leaving a faint chemical trace on a photographic plate in California. One pulsating star had provided the missing rung in the distance ladder. The known universe expanded from one galaxy into a population of galaxies almost overnight. And the object that forced that change remains visible to the unaided eye as a dim patch in a dark sky, even though its true structure stretches far beyond the Milky Way. On a clear autumn night in the northern hemisphere, Andromeda can be found as a faint blur between the constellation Cassiopeia and the Great Square of Pegasus. Under dark skies, it looks like a small patch of mist. Many people could mistake it for a thin cloud, although it remains fixed while atmospheric clouds drift across the stars. This object is also known as Messier 31. The name comes from Charles Messier's 18th century catalogue of faint objects that could be confused with comets. Messier recorded Andromeda as the 31st entry, long before astronomers understood that it was a galaxy beyond the Milky Way. The light entering your eyes has traveled for approximately 2.5 million years. It began crossing intergalactic space around the time the earliest members of the human genus were appearing in Africa. During its journey, multiple human species evolved. Modern humans spread across the planet, and every recorded civilization rose within the final few thousand years. The faint patch visible from Earth represents mainly Andromeda's bright central region. The outer disk becomes too dim for unaided human vision, even though long-exposure photographs reveal a much larger structure. Andromeda's visible stellar disk is often estimated at roughly 200,000 light-years across, with some studies extending its faint outer structures farther. The Milky Way's bright disk is commonly described as about 100,000 light-years wide, making Andromeda visibly broader by many estimates. Its long axis would cover several degrees of the sky if human eyes could detect the entire disk. That apparent width would make it several times broader than the full moon. Distance and faintness hide nearly all of it. Andromeda may contain around 1 trillion stars, although the total remains approximate. Astronomers cannot count every star individually. Many are too faint, crowded together, or hidden behind dust. The estimate comes from measuring the galaxy's total light, studying different stellar populations, and comparing those observations with models of how stars of various masses contribute to a galaxy's brightness. Near the center lies a supermassive black hole, estimated at close to 100 million times the mass of our star. Sagittarius A, the black hole at the center of the Milky Way, contains approximately 4 million stellar masses. Andromeda's central black hole may therefore hold more than 20 times as much mass. That difference does not make the whole galaxy 20 times heavier. A central black hole contributes only a small fraction of a large galaxy's total mass. Most of the gravity comes from stars, gas, and the much larger dark matter halo surrounding the visible disk. Andromeda also contains several hundred known globular clusters. These are dense spherical collections of old stars, often containing hundreds of thousands of members. The Milky Way has roughly 150 known globular clusters, so Andromeda's system appears substantially richer. 2 prominent satellite galaxies sit near it in photographs. Messier 32 is a compact elliptical galaxy positioned close to Andromeda's bright center from our viewpoint. Messier 110 is larger and more diffuse, appearing as an elongated glow nearby. Both orbit within Andromeda's wider gravitational influence. Many additional dwarf galaxies accompany the system. Some show signs that Andromeda's gravity has stretched, stripped, or disturbed them over long periods. One of the clearest records of earlier destruction is the giant stellar stream. This broad trail of stars extends through Andromeda's halo and probably formed when a smaller galaxy passed too close and was torn apart. Galactic accretion describes this process. A larger galaxy captures a smaller one, pulling away its stars through tidal gravity. The stolen stars may remain in long streams for billions of years before becoming mixed into the larger galaxy's halo. Andromeda's outer regions contain several such streams and irregular features. They show that the galaxy grew partly by absorbing smaller systems, much as the Milky Way has done throughout its own history. Its visible size is easier to compare than its total mass. Dark matter emits no ordinary light, and a galaxy's outer boundary fades gradually. Astronomers estimate mass by measuring how quickly stars and gas orbit, how satellite galaxies move, and how gravity affects surrounding material. Those measurements clearly show that Andromeda's bright disk is larger than the Milky Way's. Estimates of their complete masses overlap, however, leaving open the possibility that the two galaxies are closer in total gravitational size than their visible disks suggest. Andromeda therefore belongs to a larger system of motion. Its satellites, dark matter halo, and neighboring galaxies all influence where it will travel next, along with the Milky Way moving through the same gravitational neighborhood. Beyond Andromeda's outer streams and satellite galaxies, the Milky Way enters the same wider gravitational map. This region is called the local group. It spans roughly 10 million light-years and contains more than 80 known galaxies, with the count continuing to change as astronomers discover faint dwarf systems. Many of these small galaxies produce so little light that they are almost invisible beside the bright foreground stars of the Milky Way. Andromeda and the Milky Way dominate the group. Together, their stars and surrounding dark matter halos contain most of its mass. The third largest spiral member is the Triangulum galaxy, also called Messier 33. It lies approximately 2.7 million light-years from Earth and contains tens of billions of stars. Its disk is much smaller than those of Andromeda and the Milky Way, yet it remains large enough to support extensive regions of active star formation. One of those regions, designated NGC 604, stretches across more than 1,000 light-years. It contains young, massive stars whose ultraviolet radiation makes the surrounding hydrogen gas glow. Smaller galaxies occupy the space around these three spirals. The large and small Magellanic Clouds move through the Milky Way's outer gravitational region. Both are visible without a telescope from much of the southern hemisphere. The large Magellanic Cloud lies roughly 160,000 light-years away, while the small Magellanic Cloud is about 40,000 light-years farther. Streams of gas extend between and behind them. Their shapes record gravitational interactions with each other and with the Milky Way. The Milky Way's halo is also stripping stars and gas from several smaller dwarf galaxies. The Sagittarius dwarf spheroidal galaxy provides a clear example. It is currently being pulled apart as it passes through the Milky Way. Long streams of its former stars wrap around our galaxy, preserving the path of repeated encounters over billions of years. These interactions occur far beyond the bright stellar disks. A galaxy's dark matter halo may extend hundreds of thousands of light-years from its center. Andromeda's surrounding halo of thin gas has been detected across more than 1 million light-years in some directions, approaching the outer region associated with the Milky Way. Local gravity can hold galaxies together across these distances. Cosmic expansion increases the separation between sufficiently distant systems, while the local group remains governed mainly by the gravitational attraction of its members. Andromeda's motion has long seemed to provide a clear view of their future. Its light is blue-shifted. Blue shift occurs when light waves are compressed toward shorter wavelengths as a source approaches. After accounting for the motion of our planetary system around the Milky Way, Andromeda is moving toward our galaxy at roughly 110 kilometers per second along our line of sight. That measurement describes radial velocity, the part of its motion directed toward or away from us. A complete trajectory also requires transverse velocity, which is movement sideways across the sky. Andromeda is so distant that its sideways shift appears extremely small, even across many years of observation. A slight change in the estimated transverse motion can alter its future path by hundreds of thousands of light-years. For more than a decade, the best-known simulations predicted a major collision beginning in roughly 4 to 5 billion years. Illustrations showed Andromeda expanding across Earth's sky before the galactic disks passed through each other and eventually merged. Newer calculations have made that outcome less certain. Researchers combined more than 10 years of observations from the Hubble Space Telescope with measurements from the European Space Agency's Gaia mission. They also included the gravitational effects of the Triangulum Galaxy and the Large Magellanic Cloud. The Large Magellanic Cloud is especially important because its mass can shift the Milky Way's motion. Triangulum can also tug on Andromeda and change its future direction. In models published in 2025, the chance of the Milky Way and Andromeda merging within the next 10 billion years was approximately 50%. A direct, head-on encounter during the often-quoted period, 4 to 5 billion years from now, had a probability of only around 2%. Some simulations produce a close passage that distorts both galaxies without immediately combining them. Others create a glancing encounter, followed by a delayed merger several billion years later. Another substantial group of simulations allows the two major galaxies to remain separate throughout the full 10 billion year period. The future of the local group therefore depends on motions too small to measure perfectly, along with mass distributed through several interacting halos. Whether Andromeda eventually merges with the Milky Way or passes at a distance, the present gap remains about 2.5 million light-years. Crossing it deliberately would require a machine to survive, while the galaxies themselves continued moving and changing around it. A spacecraft leaving the Milky Way for Andromeda would begin with approximately 2.5 million light-years still ahead. At Voyager 1's outward speed of about 17 kilometers per second, the crossing would require roughly 44 billion years. The universe has existed for about 13.8 billion years, so the spacecraft would need more than 3 times the entire age of the cosmos to reach its destination. The Parker Solar Probe has traveled much faster. During its closest passages around the Sun, it has exceeded 400,000 miles per hour. That record was achieved by falling deep into the gravity of our star and sweeping rapidly around it, rather than by maintaining the same speed through intergalactic space. Even if a spacecraft could hold a similar velocity for the whole journey, a simple calculation still gives a travel time near 4 billion years. The first complex cells on Earth appeared within a comparable span. Reaching 1% of light speed would reduce the journey to about 250 million years. Earth looked profoundly different that long ago. The continents were joined within Pangaea, and the largest extinction event in the fossil record was approaching. At 10% of light speed, Andromeda would remain approximately 25 million years away. That period is longer than the time separating the earliest apes from modern humans. Half the speed of light would still produce an Earth frame travel time of roughly 5 million years. These estimates assume constant cruising speed and ignore the time needed to accelerate. They also assume the destination remains where expected, while Andromeda, the Milky Way, and the surrounding galaxies continue moving through the local group. Relativity changes the experience aboard a sufficiently fast spacecraft. According to special relativity, a moving clock runs more slowly when measured from a frame in which it is traveling at extreme speed. This effect is called time dilation. At half the speed of light, the reduction remains modest. A 5 million year journey would still last more than 4 million years for those aboard. The difference becomes dramatic only when velocity approaches light speed with extraordinary closeness. An idealized ship accelerating continuously at 1 Earth gravity for half the distance then turning around and slowing at the same rate, could make the traveler's elapsed time surprisingly short. Simplified relativistic calculations produce a subjective journey of roughly 29 years to Andromeda. Observers remaining in the Milky Way would still measure about 2.5 million years passing. That calculation describes what the equations allow under perfect assumptions. It requires an engine capable of producing continuous acceleration for years while approaching light speed. The ship would need an immense and sustained energy source, along with a way to carry fuel or receive power across millions of light years. Acceleration solves only half of the motion. The spacecraft would arrive moving close to light speed unless it reserved comparable energy for deceleration. A vessel that failed to slow would pass through Andromeda's outer regions and continue onward, crossing even a large galaxy far too quickly for ordinary exploration. Shielding would add still more mass. Intergalactic space contains fewer particles than the regions between nearby stars, though millions of years of travel would create an enormous cumulative exposure. Dust impacts, cosmic rays, and gradual radiation damage would continue acting on the hull. The route would offer almost no assistance. A journey between stars can at least aim towards systems containing energy, raw materials, and possible places to stop. The gulf between the Milky Way and Andromeda contains scattered gas, dark matter, and a limited population of isolated stars or faint systems. It provides no dependable chain of destinations for refueling or repair. A generation ship traveling at 10% of light speed would need to function for 25 million years. Closed ecosystems would have to recycle water, air, nutrients, and waste with near-perfect reliability. Every pump, seal, computer, and habitat wall would require replacement many times. Species often change substantially over periods much shorter than this. A human population isolated for millions of years could evolve under the ship's artificial gravity, radiation environment, diet, and limited genetic pool. Language would become unrecognizable. The culture responsible for launching the vessel would survive only through continually renewed records, assuming later generations still chose to preserve its purpose. Technology might be rebuilt repeatedly from raw materials carried at launch. A self-repairing robotic probe avoids the needs of a biological population, though it inherits its own long-term problems. Radiation can damage stored information. Mechanical systems wear down, while microscopic manufacturing errors accumulate unless the probe can inspect and rebuild every part of itself. Physics permits several imagined paths across this distance. None currently offers a credible machine capable of surviving the required energy demands and timescales. Andromeda appears remote enough to define an outer limit, yet it remains one neighboring galaxy. Farther away, galaxies gather by the hundreds and thousands until an entire Milky Way becomes only one point inside a larger structure. Beyond the local group, the number of galaxies begins to rise far more quickly than the distance between them. The Milky Way and Andromeda belong to a relatively loose collection. More than 80 galaxies occupy a region roughly 10 million light-years across, though most are small dwarf systems. A rich galaxy cluster contains hundreds or thousands of large galaxies bound within a much denser gravitational environment. The nearest major example is the Virgo cluster, located roughly 54 million light-years from Earth. Its exact membership depends on how astronomers define the cluster's edge and which faint galaxies a survey can detect. More than 1,000 members are known, and some estimates include well over 1,500. From a great distance, each galaxy becomes one point of light. A spiral containing billions of planetary systems may appear beside an elliptical galaxy holding trillions of stars. Yet both occupy only one small mark on the cluster map. Near Virgo's center lies Messier 87, a giant elliptical galaxy containing no bright spiral arms. Its stars move through a broad, rounded structure formed partly through earlier galactic mergers. Messier 87 also contains the first black hole ever directly imaged. In April of 2019, the Event Horizon Telescope collaboration released an image of a bright ring surrounding a dark central region. The telescope was a worldwide network of radio observatories operating together as though they formed one Earth-sized instrument. The black hole contains roughly 6.5 billion stellar masses. Hot material moving around it produces radio waves, while the black hole's gravity bends the paths of those waves before they travel toward Earth. Virgo already makes the local group seem modest. The Coma cluster creates an even denser example. Coma lies approximately 320 million light-years away, in the direction of the constellation Coma Berenices. It contains more than 1,000 large galaxies, along with many smaller members that become difficult to detect at that distance. Rich clusters such as Coma can span several million light-years. Galaxies near their centers travel at speeds reaching thousands of kilometers per second, following paths controlled by the cluster's combined gravity. The visible galaxies provide only part of that mass. The space between cluster members contains an extremely thin plasma called the intra-cluster medium. Plasma is gas heated so strongly that electrons separate from atomic nuclei, leaving electrically charged particles. This gas can reach temperatures of tens of millions of degrees. At such temperatures, it emits X-rays, rather than ordinary visible light. Space telescopes designed for X-ray astronomy can therefore map material that remains invisible in a normal photograph. The gas is thin enough that individual particles may travel long distances before colliding, yet the cluster contains such an enormous volume that the total amount becomes immense. In many rich clusters, the hot intracluster gas contains more ordinary matter than all the stars in all the member galaxies combined. Even the stars and hot gas cannot explain the cluster's full gravity. Astronomers measure the velocities of individual galaxies and calculate how much mass must be present to keep the cluster bound. The required value greatly exceeds the amount of visible matter. A second method uses gravitational lensing. Mass bends space-time, changing the paths of light from galaxies lying farther away. A foreground cluster can stretch those background galaxies into thin arcs, magnify them, or produce several distorted images of the same object. By measuring those distortions, astronomers can reconstruct the cluster's total mass distribution. The method responds to gravity, regardless of whether the source of that gravity emits light. One of the clearest examples comes from the Bullet cluster, a pair of galaxy clusters that passed through each other. During the encounter, the hot gas clouds collided and slowed through pressure, much as two thin fluids would resist one another. X-ray observations show much of this ordinary matter concentrated between the two cluster centers. Gravitational lensing maps place most of the mass farther ahead, near the galaxies on either side. The galaxies pass through the collision with relatively few direct impacts because the spaces between their stars are enormous. The dominant dark matter also continued forward, with little apparent resistance. This separation provides strong evidence that dark matter behaves as a collisionless component. In this context, collisionless means that its particles interact very weakly with ordinary matter and with one another, while still producing gravity. A cluster is therefore held together by the combined gravity of galaxies, hot plasma, and a much larger quantity of dark matter. The Milky Way would be only one member inside such a system. Andromeda's trillion possible stars would form another point nearby, and the 2.5 million light-year distance between them would become only part of the spacing inside a much larger population. Clusters themselves also move within wider patterns. Their velocities trace gravitational flows extending across hundreds of millions of light-years, where even thousands of galaxies begin to merge into one region on the cosmic map. The motion of a galaxy cluster can reveal a structure far larger than the cluster itself. For much of the 20th century, astronomers described the local group as part of the Virgo supercluster, a broad concentration of galaxies centered roughly in the direction of the Virgo cluster. That description came mainly from position. Galaxies appeared more densely gathered in that region of the sky, suggesting that several nearby groups and clusters belonged to one larger arrangement. Position alone leaves part of the structure hidden. A galaxy's light carries information about its motion through redshift. When space expands between Earth and a distant galaxy, the wavelengths of the arriving light become stretched. Spectral features that formed at known wavelengths shift toward the red end of the spectrum. More distant galaxies generally show greater redshift because more expanding space lies between them and us. This relationship is called Hubble expansion. Local gravity adds a second motion. A galaxy may fall toward a nearby cluster, move away from an underdense region, or travel sideways through a larger flow. The difference between its observed motion and the smooth motion expected from cosmic expansion is called peculiar velocity. The word peculiar means individual or local in this context. It does not imply that the galaxy behaves strangely. Peculiar velocity records how nearby gravity changes the galaxy's path. Astronomers can estimate this motion by measuring a galaxy's redshift and comparing it with an independent estimate of its distance. If the galaxy approaches faster than smooth expansion predicts, some concentration of matter may be pulling it forward. Repeating this process across thousands of galaxies creates a map of cosmic flow. In 2014, a team led by astronomer R. Brent Tully used these velocity measurements to define a vast region surrounding the Milky Way. They named it Laniakea, a Hawaiian word often translated as immense heaven. Laniakea spans roughly 500 million light-years. Estimates place around 100,000 galaxies within its mapped region. Its total mass may approach 100 quadrillion times the mass of the Sun. The boundary was identified through the direction of galactic motion. Water on a landscape flows downhill toward different drainage basins. The velocity map of Laniakea follows a related idea in 3 dimensions. Galaxies inside the region tend to move along paths leading toward a shared gravitational basin. This flow converges broadly toward the region known as the Great Attractor. The Great Attractor lies hundreds of millions of light-years away in the direction of the constellations Norma and Centaurus. Observing it is difficult because part of the region sits behind the Milky Way's disk, where stars and dust block visible light from more distant galaxies. Its name can suggest one enormous hidden object. The measured attraction comes from a wide concentration of galaxy clusters, gas, and dark matter distributed across a large volume. No single galaxy or black hole accounts for the complete motion. The Norma cluster forms one important mass concentration in this area. Nearby groups, including the local group, move at hundreds of kilometers per second relative to the smooth expansion of the universe. Farther away lies the Shapley concentration, one of the densest known collections of galaxies in the nearby cosmos. It sits roughly 600 million light-years from Earth and contains multiple rich clusters. Its gravity appears to influence motions across scales, extending beyond the immediate Great Attractor region. This makes Laniakea's boundary less permanent than the edge of a planet, or even the membership of a tightly bound cluster. A rich galaxy cluster can remain together because its internal gravity overcomes cosmic expansion. The most distant parts of Laniakea do not all share that level of gravitational binding. They participate in a present-day pattern of motion, while their long-term paths depend on distance, surrounding matter, and the accelerating expansion of space. Dark energy drives that acceleration on the largest scales. As expansion continues, some regions currently placed within the same flow map may become increasingly separated. Light traveling between distant areas will take longer to arrive, and future gravitational influence may weaken across the widest gaps. Laniakea, therefore, describes an immense pattern measured during the universe's current era. Its borders follow calculated flows and change when distances, velocities, or mass estimates improve. From within it, the local group occupies one small current. The Virgo cluster forms part of a denser branch. Other clusters move along neighboring paths through a region hundreds of millions of light-years wide. Viewed from farther away, Laniakea loses the appearance of a cosmic continent. It becomes one curved concentration within a much larger network of filaments, walls, and crowded intersections extending across the observable universe. At a wider scale, Laniakea blends into neighboring concentrations until individual superclusters become difficult to separate. Galaxies are distributed through long filaments, broad sheets, dense intersections, and enormous walls. Together, these features form the cosmic web. The filaments resemble narrow strands only when compared with the structures around them. Many are millions of light-years thick and extend for hundreds of millions of light-years. Galaxies travel along them in loose chains, accompanied by hot gas and large quantities of dark matter. Several filaments can meet at a node. These intersections contain the densest regions of the web, where gravity has gathered enough material to form rich galaxy clusters. The Virgo and Coma clusters occupy environments of this kind. Sheets spread galaxies across flatter regions between the filaments. Some sheets contain walls so extensive that their complete dimensions are difficult to define. Their edges depend on how closely galaxies must be connected before astronomers count them as part of the same structure. The Sloan Great Wall provides one example. Discovered through galaxy maps produced by the Sloan Digital Sky Survey, it extends across roughly 1.4 billion light-years under some definitions. It contains several superclusters joined through broad concentrations of galaxies. A structure this large did not begin as a completed wall. Its origin can be traced to the early universe, when matter was distributed far more evenly than it is today. Around 380,000 years after the Big Bang, the universe cooled enough for electrons to join atomic nuclei. Light could then travel freely through space, producing the radiation now called the cosmic microwave background. Sensitive instruments have mapped this ancient light across the entire sky. Its average temperature is close to 2.7 degrees above absolute zero. The map also contains tiny variations, with warmer and cooler regions differing by only about 1 part in 100,000. These temperature differences correspond to slight variations in density. Some regions held a little more matter than average, others contained slightly less. The differences were extremely small, yet gravity had billions of years to act upon them. A region containing extra matter produced slightly stronger gravity. That gravity pulled in additional material, increasing the region's mass and making its attraction stronger. Underdense regions gradually lost matter to their surroundings. Dark matter played a central role in this process. It does not absorb, emit, or reflect ordinary light in any measurable way. It still produces gravity, allowing concentrations of dark matter to begin growing while the ordinary matter of the early universe remained hot and strongly influenced by radiation. These dark matter concentrations formed an invisible framework. As the universe expanded and cooled, ordinary hydrogen and helium gas fell into the growing gravitational wells. Gas gathered most efficiently along elongated regions where several directions of gravitational collapse came together. Dense clouds formed within those filaments, cooled, and eventually produced stars. Galaxies developed along the same underlying structure. Rich clusters grew where multiple filaments intersected. The result was a web created through gravity, acting on tiny initial differences. No physical strand was stretched across space, and no central process arranged the galaxies into a pattern. The measured conditions of the early universe naturally developed into filaments and nodes when scientists reproduced them in computer simulations. Modern surveys can compare those simulations with the real sky. The Sloan Digital Sky Survey began regular operations in 2000 and used a dedicated telescope at Apache Point Observatory in New Mexico. It measured the spectra of millions of galaxies and quasars. A spectrum separates incoming light into wavelengths. Specific features reveal a galaxy's redshift, allowing astronomers to estimate how rapidly cosmic expansion is carrying it away. Combining redshift with direction on the sky produces a three-dimensional map. Early Sloan maps displayed narrow wedges filled with thousands of galaxy positions. Empty-looking regions appeared between curved bands and crowded intersections. As the survey expanded, the larger web became unmistakable. The European Space Agency's Euclid telescope is extending this work across a much greater volume. Launched in July of 2023, Euclid measures the shapes and distances of galaxies across billions of light-years. Its observations include weak gravitational lensing, the subtle distortion created when foreground matter bends light from distant galaxies. By measuring these tiny changes across large areas, astronomers can reconstruct parts of the dark matter framework supporting the visible web. At this scale, a galaxy containing hundreds of billions of stars becomes a luminous marker. Long chains of those markers reveal filaments that would otherwise remain largely invisible. The bright pattern occupies only part of the available space. Between its walls and strands lie vast, underdense regions containing far fewer galaxies, and those dark openings account for most of the universe's volume. The dark regions between the cosmic web's filaments occupy far more space than the bright structures outlining them. Astronomers call these regions cosmic voids. A void contains fewer galaxies and less matter than the average region of the universe, though it is never perfectly empty. Thin gas, dark matter, and scattered galaxies still remain inside. Many voids span tens of millions of light-years. The largest reach across hundreds of millions. Their existence follows naturally from the same process that built the cosmic web. In the early universe, some regions contained slightly more matter than average, while others contained slightly less. Gravity strengthened the difference over time. Denser areas pulled material toward themselves, feeding the filaments and galaxy clusters. Regions that began with less matter lost more of it to their surroundings. As matter flowed outward, the interiors of the voids became increasingly sparse. Their effective boundaries moved apart, making the voids expand relative to the crowded structures around them. Cosmic expansion also plays a stronger role in these low-density regions. Inside a rich galaxy cluster, gravity binds thousands of galaxies together and resists expansion. Inside a deep void, far less mass is available to slow the separation of distant objects. The result resembles rising bread on an enormous scale. Dense material gathers along boundaries, while the open regions between those boundaries grow wider. The comparison remains imperfect because cosmic voids have irregular three-dimensional shapes, though it captures how increasing separation can enlarge an underdense region. One of the best-known examples is the Boötes void. Astronomer Robert Kirshner and his colleagues identified it in 1981 while measuring galaxy redshifts in the direction of the constellation Boötes. Their survey revealed a surprisingly large region containing very few bright galaxies. The Boötes void lies roughly 700 million light-years from Earth and is often estimated to be around 300 million light-years across. Light would need approximately 300 million years to travel from one side to the other. That distance is greater than the separation between the Milky Way and Andromeda by more than 100 times. Early descriptions sometimes presented the region as almost completely empty. Later surveys found dozens of galaxies inside it, with additional faint objects likely remaining undetected. Even so, the number is extremely low for such an enormous volume. A region of comparable size in an average part of the universe would contain many thousands of substantial galaxies. The galaxies that do form inside voids can develop under unusual conditions. In a rich cluster, galaxies frequently pass near one another. Their gravity can distort spiral arms, strip away gas, or trigger mergers. Hot gas filling the cluster may also remove colder gas from a galaxy as it moves through the surrounding plasma. A void galaxy experiences fewer close encounters. It may preserve a cleaner spiral shape and retain more of the gas needed to form new stars. Some void galaxies remain small, blue, and actively star-forming because their development has been less affected by collisions with large neighbors. Others form along thin, internal filaments running through the void. These faint strands show that void interiors contain structure of their own, though the density remains far below the cosmic average. Location, therefore, influences how a galaxy ages. A large elliptical galaxy near the center of a rich cluster may have grown through repeated mergers. A small spiral inside a void may have passed billions of years with few major disturbances. Both galaxies follow the same physical laws, while their surroundings provide very different histories. The view from a planet inside a deep void would also differ from the sky seen on Earth. The local galaxy would still contain stars, nebulae, and neighboring planetary systems. Beyond its outer halo, however, the nearest large galaxies might lie tens of millions of light-years away. Their light would be faint, and many could remain invisible without powerful telescopes. A civilization developing there might first conclude that its own galaxy stood nearly alone. Discovering the wider cosmic web could require more sensitive instruments and longer observations than it did from the Milky Way's position near several neighboring galaxies. Most of the universe's volume resembles these underdense regions more closely than it resembles a galaxy cluster. The bright cosmic web receives attention because its stars and galaxies produce light. The open spaces surrounding it occupy the greater share of the map. Filaments, walls, and clusters reveal where matter gathered. Voids reveal how much space remains after gravity completed that gathering. Together, they form the largest structure we can map. The final limit comes from the distance light has been able to travel through the expanding universe, determining how much of this complete network can ever appear in our sky. The universe is approximately 13.8 billion years old. At first, that seems to place a simple limit on how far we should be able to see. Light travels 1 light-year in 1 year, so a universe this old might appear to have a visible radius of 13.8 billion light-years. The actual radius of the observable universe is much larger. The most distant regions we can observe are now approximately 46.5 billion light-years away. This gives the observable universe a present diameter of roughly 93 billion light-years. No light crossed that distance by moving faster than light. The distance changed while the light was traveling. Space itself expanded during the journey. A photon may have left a young region of the universe when that region was much closer to the matter that would later form the Milky Way. As billions of years passed, the space between the photon's starting point and its destination continued growing. By the time the photon reached Earth, the matter that released it had been carried much farther away by cosmic expansion. Its current distance can therefore exceed the number of years the light spent traveling. The oldest electromagnetic light we can observe comes from the cosmic microwave background. This radiation was released approximately 380,000 years after the Big Bang. Before that time, the universe contained a hot plasma, a mixture of atomic nuclei, free electrons, and intense radiation. Photons could not travel far through this material. Free electrons repeatedly scattered them, much as droplets of water scatter light inside a dense fog. As the universe expanded, it cooled. Temperatures eventually fell enough for electrons to join atomic nuclei and form neutral atoms, especially hydrogen and helium. This period is called recombination, although it marked the first widespread formation of neutral atoms rather than a repeat of an earlier event. Once the free electrons were removed from the plasma, photons could travel across space without constant scattering. The universe became transparent. That ancient light has been traveling ever since. At the time of release, its wavelengths were much shorter. Cosmic expansion stretched those wavelengths over billions of years until the radiation shifted into the microwave part of the spectrum. Today, the cosmic microwave background has a temperature of approximately 2.7 kelvins, only a few degrees above absolute zero. Sensitive instruments detected arriving from every direction, carrying a picture of the universe when no stars or galaxies yet existed. Tiny variations in that background became the seeds of the cosmic web discussed earlier. The map of those variations also helps scientists estimate the contents of the universe. Ordinary matter accounts for roughly 5% of the total cosmic mass energy budget. This includes stars, planets, gas, dust, living organisms, and every chemical element measured in laboratories. Dark matter contributes approximately 27%. It produces gravity and helps hold galaxies together, though its underlying particles have not yet been identified. The remaining 68% is associated with dark energy. Observations of distant supernovae in the late 1990s showed that cosmic expansion is accelerating. Dark energy is the name given to the unknown component connected with that acceleration. Scientists can measure its large-scale effect while its physical nature remains uncertain. Accelerated expansion changes what can ever reach us. A cosmological horizon is not a solid wall surrounding the observable universe. It is a limit created by distance, time, and the expansion of space. The particle horizon describes the farthest regions whose signals have had enough time to reach us since the beginning of cosmic history. Other horizons concern which events can influence us in the future, or which destinations could ever be reached by a signal sent today. A galaxy can remain visible because we receive light it emitted long ago, even if its present distance and the expansion between us make future contact impossible. As time continues, some distant galaxies will fade from view when their newer light can no longer overcome the growing separation. No larger telescope can recover information that has never had a physical path to Earth. Increased sensitivity can reveal fainter objects inside the observable region, while regions beyond the causal horizon remain inaccessible to any observation made here. The observable universe therefore describes the portion connected to us by traveling signals. The complete universe may extend vastly farther. It could be finite, on a scale far beyond present observation, or it may be spatially infinite. Current measurements reveal no established central point and no known outer wall. Every observer in a sufficiently distant galaxy would possess a different observable region centered on their own location. Their cosmic horizon would overlap with ours in some places and include regions we can never see. The map ends because light has a finite speed and the universe has a finite age, while expanding space continually changes the distances involved. From one planet inside that limited region, human instruments have still reconstructed the age of the cosmos, measured its main components, and traced its structure across tens of billions of light years. That reconstruction begins when a signal arrives. A map showing the observable universe at a useful scale could not also display Earth. The planet would occupy far less than 1 pixel. The solar system would disappear with it, followed by individual stars. On maps covering billions of light years, even the Milky Way becomes one small data point among millions of galaxies. Physical travel reaches only a tiny portion of this structure. Astronomy extends farther by collecting messengers that have already crossed the distance. Visible light carries several kinds of information. A spectrum separates that light into wavelengths, revealing lines produced by particular atoms. Hydrogen leaves a different pattern from oxygen or iron. A shift in those lines shows motion along our line of sight, while cosmological redshift helps trace the expansion of space. Parallax supplies distance for nearby stars by measuring their small apparent shift as Earth moves around its orbit. Gravitational lensing reveals mass through the way. Foreground gravity distorts more distant galaxies. Slight changes in arriving light become measurements of composition, motion, distance, and hidden matter. The European Space Agency's Euclid telescope has been conducting its main survey since February of 2024. It records galaxy shapes across large areas of sky. Tiny shared distortions in those shapes reveal weak gravitational lensing caused by dark matter between the galaxies and the telescope. In June of 2026, the Vera C. Rubin Observatory began its 10-year legacy survey of space and time from Cerro Pachón in Chile. Its 3.2 billion pixel camera can photograph a wide section of sky in one exposure. Repeated images will reveal supernovae, moving asteroids, variable stars, and gradual changes across billions of distant objects. The Nancy Grace Roman Space Telescope was scheduled to launch on August 30th, 2026. Its wide-field infrared camera is designed to survey areas at least 100 times larger than Hubble can capture in a single view. Roman will study dark energy through galaxy distributions and exploding stars, while gravitational microlensing will reveal planets whose gravity briefly magnifies background starlight. The James Webb Space Telescope is already observing from a region about 1 million miles from Earth. Its infrared instruments detect light stretched by cosmic expansion, allowing astronomers to study galaxies from the early history of the universe. Infrared observations can also pass through some dust clouds that block visible light. Light provides only one route. When black holes or neutron stars merge, they disturb space-time itself. Those disturbances travel outward as gravitational waves. The LIGO detectors in the United States, Virgo in Italy, and Kagra in Japan measure changes in length far smaller than an atomic nucleus as a wave passes through their instruments. Much longer gravitational waves can be studied through pulsars. These rapidly rotating neutron stars send radio pulses with extremely regular timing. Networks such as Nanograv compare arrival times from many pulsars. A shared pattern of tiny timing changes provides evidence for a background produced largely by pairs of supermassive black holes. At the South Pole, the IceCube Neutrino Observatory uses thousands of light sensors buried within a cubic kilometer of Antarctic ice. Neutrinos interact so weakly with matter that they can escape dense regions where ordinary light is absorbed. When one occasionally strikes a particle in the ice, the collision produces a faint flash that reveals its direction and energy. Cosmic ray observatories measure charged particles arriving from extreme environments. Magnetic fields bend their paths, making their origins difficult to trace, though their energies reveal natural accelerators far beyond anything constructed on Earth. These messengers expose different parts of the same reality. Together, they have revealed a universe whose dominant components remain unexplained. The particle identity of dark matter is unknown. The physical nature of dark energy remains unsettled. The earliest instant associated with cosmic inflation lies beyond direct observation, and the total size of the universe may exceed the observable region by an unknowable amount. Humanity occupies no visible fraction of the largest map. Our machines cannot cross most of the distances they measure. Yet a photon released before Earth existed can finish its journey inside a detector built from materials found on this one planet. That is the terrifying truth about our size. The universe can erase every physical trace of our world from the picture, while a species living on that world learns how to reconstruct part of the picture anyway.